Hibernation refers to animal species undergoing a period of significantly reduced activity and metabolic depression, typically during colder months. Characterized by low body temperature, decreased heart rate and breathing, and a slowed metabolism, hibernation was previously considered a trait specific to deep hibernators, such as rodents. However, this definition has changed and is now identified by active metabolic suppression. This includes animals like bears and recognizes that the processes of daily torpor and hibernation lie along a continuum sharing similar mechanisms. The main reason animals hibernate is to conserve energy when there's a scarcity of food. This is achieved by decreasing their metabolic rate and body temperature, allowing them to stay in a dormant state for extended periods. This period can stretch from days to months, dependent on species, environmental temperature, the time of year, and an individual's overall health. Prior to hibernation, animals stock up on energy in anticipation of the long, inactive period, often gorging themselves on food to build up fat deposits in their body. Certain species even go through hibernation whilst pregnant, birthing their young either during or right after this dormant period. An example of this is black bear females, who hibernate throughout winter to provide a warm and care-filled habitat for their newborns. Their weight significantly increases before hibernation to create the most optimal conditions for their offspring, losing 27 of this pre-hibernation weight during the period as they use their stored fats for energy. Contrarily, reptiles, invertebrates, and ectothermic animals utilize the concept of dormancy in a similar fashion, with each group having unique terminology for their dormant period. In the same vein, hibernation patterns vary among different mammalian clades, which has led to different terminology to describe these variations, such as obligate and facultative hibernation. Notably, bears primates, representatives of whom were traditionally not thought to hibernate, have recently been included in the dialogue of hibernation, adding depth and complexity to our understanding of the concept. Hibernation, a unique process marked by periods of deep sleep, broken occasionally by short spells of warm awakenings, where heart rates and body temperatures return to their usual levels. Deciphering the reason behind these awakenings has always been a mystery to scientists. There are several prevailing theories, one of which suggests that these animals need to raise their body temperature to catch up on sleep debt during hibernation. This theory is backed up by studies on Arctic ground squirrels. Some other theories suggest that these intervals serve to replenish energy or trigger an immune response. Hibernating creatures can endure extremely low temperatures. Arctic ground squirrels, for example, have been observed with an abdominal temperature as low as 2.9 dec for over 3 weeks at a stretch, although their head and neck temperature remain around 0 dec. Hibernation can be categorized into two types based on triggers: obligate hibernation, which begins with seasonal cues, and facultative hibernation, which is a response to a harsh environment or lack of food. The contrast between these two can be seen in the habits of the white-tailed prairie dog, an obligate hibernator, and its close relative, the black-tailed prairie dog, a facultative hibernator. Hibernation was once thought to only occur in rodents like ground squirrels until it was discovered in the fat-tailed dwarf lemur of Madagascar. Interestingly, these lemurs hibernate in tree holes for the majority of the year, unaffected by the peak summer temperatures of 30 degrees or more. The success of hibernation for this lemur is determined by the insulation provided by its tree hole. The authenticity of hibernation in bears was once a contentious topic, as bears showed only slight drops in body temperature compared to the dramatic reductions seen in other hibernators. However, recent research has challenged this notion. Bears not only hibernate, but also have a remarkable ability to recycle their proteins in urine, which in turn prevents muscle atrophy. Despite spending months in inactivity without food or water, hibernating bears are surprisingly able to stay hydrated using their own body fat. And, astoundingly, they manage to resist osteoporosis, maintaining their bone mass. This narrative aims to delve into the remarkable phenomenon of hibernation present within the animal kingdom, especially focusing on the dichotomy between different mammals, birds, and ectothermic creatures. The pioneering 1977 research carried out by G. Edgar Folk, Jill M. Hunt, and Mary A. Folk illustrated that small hibernators' reduced relaxation QQU interval was identical among 3 different bear species. Furthermore, a seasonal change in the Q interval was observed for typical hibernators and bears. This research is seen as one of the first to establish the hibernation behavior in bears. In a more recent study in 2016, Alina L.E. Evans, a wildlife veterinarian and associate professor at Inland Norway University of Applied Sciences, examined 14 brown bears over 3 years, investigating a range of elements such as heart rate, body temperature, and physical activity to understand the drivers leading to hibernation. The study revealed that the onset of cold weather and snow triggered bears to enter their dens. However, a decline in physical activity, heart rate, and body temperature kicked in weeks earlier. Evans noted metabolic suppression taking place during hibernation. Just before the hibernation ended, the bear's body temperature increased, which interestingly did not correlate with a rise in heart rate variability, but was triggered by the ambient temperature. Furthermore, the concept of hibernation extends beyond mammals. Historically, it was believed that swallowbirds hibernate, fueled by anecdotal findings in Gilbert White's 1789 book, The Natural History of Selborne. However, modern understanding stipulates that birds don't typically hibernate, but enter a state of torpor, with the common poorwill species being an exception. Conversely, ectothermic animals, such as fish, reptiles, and amphibians, that lack the ability to regulate body temperature actively, cannot truly hibernate. They do, however, exhibit dormancy or brumation due to decreased metabolic rates in colder or low oxygen environments. An interesting study by David Sims in 2003 debunked myths about the hibernation of asking sharks, indicating that the sharks migrated extensively in different seasons instead. In a nutshell, while hibernation might be a well-known phenomenon, the variety and complexity of the mechanisms behind it make it a fascinating area of research across the animal kingdom. Exploring hibernation induction trigger, HIT, proteins and the power of recombinant protein technology. Hibernation induction trigger, HIT, proteins, isolated from mammals, serve as vital tools in understanding the dynamics of organ recovery rates. Despite a 1997 study debunking the potential of delta-2 opioid and HIT proteins to expedite heart tissue recovery during ischemia, these proteins and their precursors have been proven significant in preserving the function of veterinary organ. Thanks to the progress made in the arena of recombinant protein technology, the manufacture of HIT proteins in laboratories no longer requires animal euthanasia. This bioengineering approach doesn't just protect mammalian species that produce these valuable proteins, but also enriches our research capabilities by revealing key elements like the 1-glycoprotein, like 88 key to hibernation related protein. Here, a testament to this approach was showcased in a 2014 study where recombinant technology was leveraged to construct, express, purify, and isolate animal H20, 25, and HPT 25 and H27 proteins in order to better comprehend essential hibernation proteins. Hibernation in humans has been an area of high interest for researchers, holding potential benefits like life preservation of critically ill or injured individuals by placing them in temporary hibernation until proper treatment is available. In addition, hibernation in humans is being seriously explored for facilitating space journeys, including potential missions to Mars. The possibility of hibernation in ancient hominid species is also an area of ongoing investigation for anthropologists, with terrestrial living and its intense seasonal shifts playing critical roles in both bird and mammalian life. Some researchers suggest that the exposure to seasonal pressures eventually led to the development of hibernation. This theory stands true for all animal families that undergo winter dormancy, with the duration of hibernation usually increasing with more pronounced seasonal variation. Multiple instances of evolution of hibernation in endothermic animals have been recorded, with at least one occurrence each in mammals and birds, providing further evidence of its impact. Following the divergence of torpor and hibernation from a shared primordial ancestor of birds and mammals, it became evident the capacity to hibernate or enter torpor would be relinquished by most sizable mammals and birds. This is attributed to the fact that as animals increment in size, their surface area to volume ratio diminishes, thereby requiring less energy to maintain high internal body temperature, rendering hibernation unnecessary. The evolution of hibernation seems to manifest differently in marsupials and placental mammals, yet this remains disputed. Evidence indicates that youthful marsupial hibernators gain the ability to regulate their own heat and subsequently hibernate, whereas placental mammals that hibernate initially achieve their morgulation, developing the hibernation ability later. Though disputable, this disparity in development suggests evolutionary distinction. In reptiles, ectothermy, Lack of a system for managing low temperatures would lead to fatal outcomes in many ecosystems. Reptiles evolved rumation, a winter dormancy, to mitigate cold conditions. Modern reptiles displaying winter dormancy exhibit higher survival rates and slower aging. Moreover, these reptiles deliberately lower their internal body temperatures in comparison to mammals or birds who prepare for but don't intrinsically induce hibernation. They actively seek cooler environments based on an inbuilt cyclic clock, which likely corresponds to external temperature fluctuations. A survival mechanism during hibernation called hypercapnic acidosis is shared between reptiles and mammals, a possible instance of parallel evolution. On the other hand, seasonal diapause, the winter dormancy of arthropods, appears plastic and rapidly evolving, marked by extensive genetic variation and substantial natural selection occurrences across several arthropod classes. As hibernation typically evolves in response to increased seasonality, the diapause mechanism was developed as a means to curb energy consumption, especially in harsh environments. While also timing their active or reproductive periods, the evolutionary progression of seasonal diapause is believed to have transpired in 3 distinct stages. The predominant theme of the narrative pertains to the distinct adaptive mechanisms of seasonal dormancy in different fish species, despite sharing a common cold environment. Notably, unlike the majority of animals entering winter dormancy that decrease their metabolic rates, certain fish, for instance, the cunner, defy this pattern. These fish rather dampen their activity levels than forcefully reducing their fundamental metabolic rate. This implies they rely on their lack of movement and the cold water temperature to lessen energy use, yet their inherent rate of metabolism remains unchanged. However, this differs in fish like the Antarctic yellowbelly rock cod, Notothenia cordyceps, and those hibernating under oxygen-deprived conditions, all of which display a metabolic suppression akin to other dormant winter animals. Still, the biological progression behind the evolution of this metabolic suppression in fish remains an enigma. It is observed that fish entrapped in winter slumber conserve ample energy by remaining motionless, leading to the lack of strong evolutionary pressure to form a similar metabolic suppression mechanism necessary in oxygen-deficient situations.